All right, so at this point, after we have mastered our skill in taking square root and understanding what square roots are, and so now we're going to advance to learning about the nth root right here, and we're going to learn specifically in this lesson how we can calculate the nth root of some number. All right, so to begin with the idea, allow me to bring in a couple of the following computation problems right here. All right. So what I have introduced here, what I have here as an introduction here is so we have a number 27, and then we have this symbol right here that stays on top of that. So it looks like a square root, and so that's why, like I said earlier, this lesson must be learned after you have learned and mastered your skill about square root. But so this symbol right here looks like a square root, but it has a little superscript here. The way how we verbalize that, this is called the cube root. Okay, that 3 right here, that 3 superscript is called a cube root, okay, of 27. So of course we're calculating the cube root of 27. Okay, and so now for this work right here specifically, okay, before taking the cube root, I think of the 27. So just like how we were doing square root. So square root is when if the number inside the root is a perfect square, then we take the square root giving me the number. So we're going to try our best to see if this 27 here can be expressed as a cube. And the way it says right here, cube roots. Okay, and so that rings a bell right here. So now 27 is actually recognized as a 3 cubed, a perfect cube of 3. 27 is a perfect cube of 3. And now cube root of 27, the answer comes out being just simply 3 right here. Okay, and so that's one little problem. All right, so how about another introduction problem right here? How about this one right here, the way how I say it, and it looks very similar to the one I brought up earlier, but now that root sign has a superscript 5 right here, and the number inside of that is a 32. So here's the way how we're saying it, how we verbalize it. All right, as far as pronouncing it or saying it, this is called the fifth root. The superscript 5 right here is a fifth, indicating so it's a root sign, but it's now the fifth root of 32. That's what we're looking for. And so now think just as closely as you can with how we were doing the earlier problems and with the days we were doing square roots. So now this 32 right here, we are taking fifth root. So let's see if we can express the 32 here as a perfect fifth power. So right now I'm holding on to the fifth root, but 32 itself, yes, I can recognize that as a 2 to the fifth power. So we asked ourselves, we questioned ourselves, is there a perfect fifth power, that makes 32? And so yes, that was 32 is a perfect fifth power of 2. And so now fifth root of 2 to the fifth, the answer comes out being 2. And so just like that, now for this specific one right here, the way how it says, needless to say, this is called the fourth root of 16. All right, it's the fourth root of 16. And the way to calculate it, first, let's recognize whether we can express, let's see whether we can see the 16 here. Let's recognize 16 here as a perfect fourth power. So fourth root of 16 is indeed the perfect fourth power of 2. So 2 to the fourth power equals 16. So once again, what I have done, I have re-expressed 16 here as 2 to the fourth, or I understand 16 as a perfect fourth power of 2. And so fourth root of 2 to the fourth power, the answer comes out being 2. All right, so after a few quick calculation tries to have some general idea, now we are ready to formulate an actual definition of what it means by being an nth root, a general nth root right here. So we have seen from the cube root, a fifth root, and a fourth root, and there expectedly there's going to be seventh root, ninth root, 10th root, or whatsoever root right here. Okay, so let's come up with a generalized definition. All right, so what I have on my computer screen now is the general definition of what it means by being a general nth root. So the nth root of a number a equals a value m if, the way how it was done on the board earlier, if m, the final value raised to the n power, equals a. All right. And so my recommendation is that anytime now when we're working with the general nth root right here, think as closely as you can. Anytime you're working with an nth root, think as closely as you can, think as closely as possible with the time when we're working with a square root right there. And so now let me make that connection. So from our earlier learning about square root previously, then the square root of a equals a value m if the square of that final value m equals a. And so now switching and now transitioning this definition from a square root that we've learned and hopefully mastered, transitioning that into the general nth root. So now I'm talking about some nth root of a number a equals a final value m if the nth power. So when it was square root, then we need to verify the square of that final value to equals the number inside the root. And so now when it comes to the nth root right here, we need the final value after raising to the power n right here, which equals the number inside the root. So the way how I'm seeing it, there is generality, I mean there's the similarities that's going on between the two right there. So we specifically learn from the square root, and then we making our transition into the more generalized, the general nth root right there. Okay. And so now, needless to say, in the way how it was, and I've been saying that the square root is what we started out with, and now we're making our way transitioning into the general nth root. And I keep saying the general nth root as the more general case. So now looking back a little bit at square root right here. Yes, let's say you have a square root of 4, for example. Okay, or generally square root of a number. Okay, so now technically square root of 4 means see the root to the superscript 2, because general nth root, like a cube root, I put a little superscript 3. This is cube root, okay, of a, and then this is fourth root. I put a superscript here. And so technically square root was a root with a little superscript 2, but conventionally worldwide right here, as a worldwide convention, then we just skip that. Okay, so square root 4 is formally written as this. We skip the 2 right there, but in theory it should be there. Okay, and so just like that, generally, yes. Generally square root of a is precisely some root to the order 2, the second order, so square root of, okay, or second order root of a. Okay, and that's the way how we're seeing that. All right, so right after we've learned and just started ourselves into the general nth root right here, we have now we are now ready to apply our understanding right into the first example right here. All right, so in this example right here, let's evaluate this root expression right here. Okay, so the instruction here is saying that, hey, so we want to compute the final answer, evaluate. Now we have 64 here, but we're supposed to take the cube root. So the way how I'm seeing it, take the cube root of 64. Okay, and so the definition gave us a way of getting into answering this. So now I'm seeing 64 as 4 cubed. So now taking the cube root of 4 cubed right here, we're coming out with the answer being 4. All right, and then once again, let's check with our understanding from the definition right here. See, the cube root of 64 equals 4 because, the way how I'm seeing it, because 4 raised to the third power, right? See, this is because, even though you're not required to do this, this is just thought process, because 4 to the third power equals 64. Okay, so once that final answer here raised to the third power, right, matching with our the root order right here equals to the number inside of the radical symbol right here, then we're looking at this 4 right here is our final answer. Okay. All right, so now in part B of this example 1 right here, we are asked to find the cube root of 25. Okay, so once again, in our thought process, tentatively, the idea is to look for some number a, so that cube of a will equal 25. Okay. However, now further, let me remind anyone watching the video lesson here one specific technique that you should have learned prior to entering this class right here, this course we're taking right here, that prime factorization. So prime factorization of 25 can only put 25 as a perfect square of 5. Okay, so in prime factorization, after prime factorization, 25 can only be expressed as a perfect square. And so looking for the cube root, looking for a value a so that cubic of a, the cube of a equals 25 is now becoming challenged. Okay, and so think about it. It's going to be the same as cube root of 5 squared. Okay, cube root of 5 squared. But from the experience we've had from part A right here, we want to find a perfect cube. Our best resource right now, our best way of approaching it, trying to see the number, how we can write this as a perfect cube, but we haven't been able to. Okay, so I am not saying that the answer doesn't exist. I am not saying that the answer doesn't exist, but allow me to swing over to the computer and do a quick illustration. All right, so now think about using a calculator. We can take the cube root of 25. And really, I am not intending to teach how to use a calculator to calculate the cube root of 25 at this moment right here. So I'm just illustrating that now taking cube root of 25, the answer won't come out a nice looking value. The answer here that you can see on the computer screen with using my calculator is 2.92 for a very lengthy decimal expression right here. And I have made my explanation earlier. So basically the biggest challenge here is that we fail to express that 25 here as a perfect cube. Okay, and so the 2.9 something that you have seen on the computer screen is the value where, think about theoretically, if you can take the real perfect cube of that 2.94 something from the computer screen, then you will arrive at 25. But so that means what? The real answer for a cube root of 25 is going to be a very lengthy decimal expression. So we don't want that kind of answer. So in that way, we're just going to stay. Since we are trying to avoid a lengthy decimal expression, this cube root of 25, I can say that, hey, the best way we can write it is to keep it the same. And this is called the exact expression. And so I'm saying that, hey, this cube root of 25 is irreducible. It's irreducible. So it has a known value, but it's very lengthy in the decimal. So we avoid writing that. So we keep that in the exact expression. So this final expression right here is called exact expression. Okay. And of course, of cube root of 25. Okay. And so by far at this point right here, then again, calculating cube root or generally any nth root, we're relying on that definition that we must be able to recognize our value as a perfect nth power. So here cube root, we're trying to recognize our number as a perfect cubic power. And then if it's a fourth root, we have to recognize our number as a perfect fourth power. And so same way with how we learned about square root before, taking the square root of a value in order to expect a nice final outcome, we have to be able to see the number as a perfect square. Okay. All right, so now allow me to bring in a demonstration problem so that, once we've learned through our way to solve the demonstration problem here, we can hopefully come up with some generalization, some generality, or maybe some more details in our learning right here. So let's say here we're asked to take the cube root of negative 64 in this problem number 1 right here. So yes, you can think of that as just simply, hey, let's evaluate the cube root of minus or negative 64. Okay, so I'm seeing the answer here as minus 4. The answer to this is negative 4. Now, what's the reason for that? That is simply because minus 4 all cubed, the power 3 of negative 4 equals negative 64. Okay, and notice how I used parentheses here. Parentheses were grouping around the entire negative 4, so negative sign is included in the power. So I'm talking about negative 4 times negative 4 times negative 4, and that's how multiplying three negatives gave me a negative, and then 4 times 4 times 4 is a 64. And so we have a happy answer here. Cube root of a negative 64 equals negative 4. And then think of another problem. Okay. What I have here, fifth root of minus 32 here. I'm saying that the answer here must be negative 2. Okay. Once again, I mean, what's the number so that raising to the fifth power equals negative 32? And I'm seeing that it's negative 2 is the number. So simply the reason for that is because minus 2 or negative 2 to the fifth power equals negative 32. And again, very similar with the argument I've made earlier in that earlier little problem. Then I'm talking about minus 2 times minus 2 times minus 2 times minus 2 and times minus 2. 5 negative 2 multiplied together. And that's how I ended up with negative 32. Okay, so this is some special feature about some general nth root that is being different with square root right there. So we have mastered square root, and we've after learning thoroughly about square root, and we have been keeping our strict requirements that we cannot take the square root of a negative number. But now when we're moving on to those other roots, more general and higher order, like cube root or fifth root, we can take roots, right? The nth root of some negative numbers. Okay? But the story doesn't end here. So what I have here in the same problem number 1 right here, I'm trying to put a negative number inside of an nth root right here. What I'm looking at here is let's evaluate the fourth root of negative 16. Okay, is the answer, I'm putting question mark here, is the answer negative 2? If the answer would be a negative 2, then that means negative 2 to the fourth power must equal negative 16 tentatively. But let's find out. Negative 2 to the fourth power is indeed truly negative 2 times negative 2 times negative 2 times negative 2. 4 negative values multiplied together. So needless to say, the rule for algebra, it's going to be like positive 16. So positive 16 here is unfortunately not that number that we had inside right here. So guess what? Negative 2 here is not the answer. Okay? Then we can change our mind and think, what about, can that be equal to 2? We're putting question mark here. And so now let's test it out again. From the definition, we need 2, the final number right here. If we claim that this is the answer to the fourth root of negative 16, then 2 to the fourth power must be equal to negative 16. Let's find out. 2 times 2 times 2 times 2. 4 positive 2 values multiplied together. The answer comes out positive 16, not negative 16. Okay, so now our ultimate conclusion on this specific little problem right here, taking the fourth root, notice how the root here is being with an even order right here. So a lot of time people, including me, call that the even root. Okay, so taking the even root of a negative number, the answer here, we don't have an answer. We call that it's the undefined right here. Okay, we have an undefined value right here. Okay, at least it's not a real number. So let's open the parentheses here. Undefined means we cannot come up with an actual value. So we're saying not a real value. All right. So taking the fourth root in this problem right here, we took a fourth root, but more generalized as a more general case right here. We're taking an even root on a negative number. For this quick demonstration right here, we ended up with an undefined. Okay. And so after concluding that result right here, allow me to bring in one more little demonstration problem, still in problem number 1 right here. All right, so now we're looking at square root. So it's the sign for square root right here. We're skipping that superscript 2. So the square root of -9, we have learned and we have become well fluent with this. Square root of -9 is an undefined value. It's also not a real value. All right, so we have seen this back in the lecture, the lesson that we were learning specifically about square root. So we cannot, one cannot take the square root of a negative value right here. So meaning we come up with an undefined final answer like that. Okay, but now I brought in square root and I brought in fourth root right here. We're generally looking here at even root. Square root is now being square root after being put in the general family of nth root right here. Then square root here is an even root. Fourth root is an even root. We have sixth root out there. We have eighth root out there. We got 10th root out there. Those are all even roots like that. Okay, and so look at the answer. Even root cannot take we cannot take the even root or an even root of a negative answer. Whereas, now switching our attention back to this side of the board right here, we were primarily doing odd roots right here. So for odd root right here, it was possible to take the odd root of a negative number inside. Okay, so now that is now enough for us to come up with a solid generalization here. And let's turn over to the computer screen. All right. So when it was square root that we've learned previously, then one cannot take square root of a negative value, strictly just that, and it has never changed. This rule is the way how it is. But now when we're talking about some general nth root, which is including the square root, okay? So now it depends on the case of our order of the root right here, all right? And so now when the nth root is an even root right here, and more generally we're writing that when n is an even number, then the nth root of a is a real number, or we say it's a defined value only when the number inside here is a positive value. Okay? So real number only when we are under that requirement like that. The value for a inside the root is a positive or equals 0. So that's happening when n is an even number. Okay, and so same case right here, when n is an even number but the value inside the root is negative, then we're gonna end up with an undefined value, or the final outcome is not a real number. So we have undefined if a is negative. But then when we turn our attention over to when n is an odd number, like what we've seen on the board earlier, then nth root of a is a real value or being defined anywhere for all values of a. All right, so that has demonstrated all cases of how we can generally remember about taking a general nth root like that. So even roots like this. Okay, the short way of saying it's right after what we've learned on the computer screen right there. Even roots, we cannot take negative number. We cannot take even root of a negative number. But even root will work just fine with positive number or 0. Okay. Whereas odd roots right here, yes, it works just fine with negative numbers. Negative number is positive number going inside of an odd root. It works just fine. It will come out with a final solid value like that. All right. All right. So just now I wrote on the board right here a result that we can generalize from learning about square root. So back in square root, we were saying that hey, a square root in general has the higher priority in the order of operation. So talking about order of operations, when root is being involved and together with other operations like multiplication or division or addition or subtraction, then square root back then that we've learned is of higher priority compared to multiplication and division. And so it's going to be exactly the same way here. So we have been making a lot of similarities between a general nth root and the square root. So just like what I was saying earlier, as closely as we can with those days when we were working with square roots. But so here, an nth root is of higher priority than multiplication and division, unless each of these multiplication or division is grouped. Okay, and I will get into more details to explain this statement about unless each of these is grouped. And so allow me now to bring in an example. All right, so in this example over here, we're asked to evaluate this expression right here. So what we're seeing here, what we're realizing here in this expression is we have roots of cube root of 8 specifically in products with fourth root of 81. Okay, and so now that understanding I've written down on the other board is going to be applied here. So we have roots being mixed together, right, with multiplication. So now we have to take care, we have to find out the value of these roots first, because just like what that generality was pointed out, right there, roots will generally have higher priority than multiplication or division. So there's multiplication here mixed together with roots. And so here, in the way I'm seeing it, we have to calculate completely the two separate values for the two roots here. So think about simultaneously. In the next step, simultaneously, cube root of 8 is a 2. Because I can think of 8 here as a 2 cubed. So taking the cube root of 8 brings me down to a 2. Simultaneously, I can do the fourth root of 81 is a 3, simply because 81 can be thought of as 3 to the fourth power. That's 3 to the fourth power. Okay? And so now these two values came out simply because I took the two root values first. So I took the cube root of 8 and simultaneously at the same time I took the fourth root of 81. So now after getting the two root values successfully done right here, now I'm going to multiply. And that's how I illustrated. Multiplication comes after taking root. So now 2 times 3 equals 6. All right, so in another problem, we are asked to evaluate the fourth root of 10,000 over the cube root of 125. Okay, so to make it really clear about this evaluation problem right here, think about the fraction here as a division, because anyone learning in this video lesson is well familiar that a fraction represents a division problem. So really, we have fourth root of 10,000 divided by the value of cube root of 125. Okay, but now rewriting this expression in as a division problem right here, now we realize in this entire problem to evaluate, we have roots involved together with division. And so once again, that's generality I've pointed out earlier. We must take the root before doing either multiplication or division. In this problem here, we're having a division. And so now think about the next step. Simultaneously, I must obtain the value for these two separate roots first. Fourth root of 10,000 will become simply 10, because quick explanation, 10,000 is understood as the fourth power, a perfect fourth power of the perfect fourth power of 10. That's why fourth root of 10,000 gives me 10. Simultaneously, on the other hand, right here, cube root of 125 gives me 5. Simply that answer is because 125 is known to be the perfect cube of 5. Like that. All right. And so now after obtaining the two separate root values, that meaning root was done first, all roots was done and calculated first. Now we divide the two right here in that specific order. So 10 divided by 5 is now coming out as easy as just 2. All right. So once again, these problems right here in this example 2 really demonstrated that idea that any root right here must be done prior to taking taking multiplication or division. All right. So now in part C of the example, now what I have here is a fourth root of a 3 times 27. So the way how you're seeing it, this product 3 times 27 is put inside of the fourth root. So what it means, really what it means here is that 3 times 27, the multiplication between these two numbers is grouped together, and then that final outcome, we're going to take the fourth root on top of that. Okay, and so now this is where, that final statement of mine in that generality I pointed out earlier comes in and applies here. Unless each of these operations, right, unless the multiplication or the division is grouped, and that's what it meant in the way how it was writing right there. And so in this case right here, unless being grouped like this, right? So now we're being in a group situation. So group means we put things in parentheses. So parentheses will permanently be at the highest operation. And so this multiplication being grouped inside parentheses, we have to finish calculating what's inside here first. And so in that way, my next step, 3 times 27 is an 81 right there. Now we take the fourth root, because once again, according to the order of operation, whatever being grouped together, we have to finish that first. So 3 times 27 this time is being grouped together, even though it has multiplication. But again, grouping was increasing its order. So 3 times 27 came out with 81. Now after that, we take the fourth root of 81. That gives me the answer being 3. And once again, coming up with this answer so quickly simply because this is just now thought process right here, because 3 to the 4th power, right, equals 81. I understand 81 here. I see 81 here as the perfect 4th power of 3. All right, another problem in example 2 right here. Let's call that part D of the example. But what I'm looking at here, hey, let's evaluate the fifth root of 160 over 5. So what we're doing here is a fifth root, but we have a fraction inside. Okay. So anyone learning from in this lesson right here is well familiar that a fraction represents a division. So in that way, let's make it easier for us. Let's rewrite it first of all. So what I'm having here is a fifth root of 160 divided by 5. So now we have clearly a division, the division operation existing inside of our root. The division here really means the way how it means is that 160 divided by 5 is grouped together. So even though in the written form like this originally it was not grouped in parentheses, but that's how we understand about it like that. That it means 160 divided by 5, and then whatever that outcome will be, because now the division is grouped together. And so now after that, we take the fifth root on top of that. Okay, so now the grouping increases the order of that operation. So we must now do that before taking the fifth root. So after giving some explanation on that, the meaning right there, now we can go 160 divided by 5. It gives me 32. That comes out from 160 divided by 5. We took that operation first. Then we take the fifth root. Then the answer comes out being 2. And with that answer, I have arrived so quickly simply because I see 32 as 2 to the 5th power. So it's always been that. Now, anytime taking an nth root, we trying our best, right, to see the number there can be expressed as the perfect power that matches with that root order. Okay. All right, so now we're looking into another generality about taking an nth root here in terms of order of operation. So back in square root here, we have learned that taking square root as an operation is of higher priority than addition and subtraction like that, unless any one of those is grouped together. So we're going to take that generality and apply that to nth root, and yes, it comes out exactly the same. So what I have here as a generality, an nth root is of higher, so square root is one of those general nth roots. So an nth root in general is of higher priority than addition and subtraction, unless each one of those, right? Each of these two operations right here is grouped. Okay, and so All right, so to illustrate the idea, that generality we've learned from what I've written down on the other board right there. So now let's evaluate this in our example 3, part A right here. We want to evaluate the following expression. Square root of 36 minus the fourth root of 625 right there. Okay, square root of 36 minus the fourth root of 625. Okay, so now applying that generality that we've had on the written down on the other board into this problem. So now I see there are two separate root operations being involved together with a subtraction right here. Okay, so now carrying that generality into this problem right here, I have to finish out the two root operations here first, because again, root operation, an nth root is of higher priority than subtraction. Okay, so in that way, square root of 36, it's a 6, simply because I see that as 6 squared equals 36. So square root of 6 is now found here. Simultaneously, fourth root of 625 comes out being 5. That answer here is simply because I see 625 as the perfect fourth power of 5. So 625 is the perfect fourth power of 5. And that's why taking the fourth root of 625 gives me 5. Now after taking the two simultaneous root values right here, now I can subtract between the two. Alright, and so now that final answer comes out being simply just 1. So this part A of the example really demonstrated and illustrated that idea that roots are taken before subtraction or addition. Alright, so part B of the same example over here, another problem where I want to illustrate. We have root operations, two root operations involved together with an addition problem. And so once again, any general nth root is of higher order than addition or subtraction, or you can say the higher priority than subtraction and addition. So here I have additions being involved together with roots. And so now I'm seeing that the way how I'm doing it, I must finish out calculating the cube root of 64. Cube root of 64 comes out being 4. And that is simply because 4 cubed equals 64. That's what explains for this. Simultaneously, aside from doing that root, I have another root that we can do at the same time right here. Simultaneously, think about the fifth root of minus 32 right here. The answer will come out being minus 2. Negative 2 is the answer to fifth root of 32, simply because negative 2 to the fifth power equals minus 32. Okay. And so now after having these explanations and coming up with the two simultaneously root values right here, our next step here is just to simply add the two root values. So now think of these as the two root values. We're adding those. The answer comes out being positive 2. All right, and that's how we're doing it for another problem right here. So the two problems in part A and B of this example over here have been illustrating that idea that we must take roots before addition or subtraction. All right, but now what we're having here is, hey, let's evaluate cube root of, inside of the roots, we have 50 plus 14. So if we're observing that a little more closely, we can see that the 50 plus 14, this operation is being completely contained inside of our root. So that means what this means is that we're looking at 50 plus 14 being grouped together as one operation, being grouped together. Okay, and then whatever result that is, we will take the cube root. And so that's what it means right there for the 50 plus 14 inside of the root. So now upon realizing that everything inside the root here means we need to group all of those together. So now, according to that generality I've had on the other board, unless these operations, it refers to either the addition or the subtraction, unless any of those is grouped, then the grouping will increase the priority. So now grouping has become the first highest priority. Right? Then we take the cube root. So in that way, 50 plus 14 is giving me 64. So we did the grouped operation first. And then after that, we take the cube root. And now the answer comes out being as simple as just 4. Okay, and that is simply because 4 cubed will equal 64. That is our answer to that particular problem. All right, so now in part D of our example here, let's look at fifth root of 47 minus 15. And so what I'm having here is we have subtraction being involved together in one expression with the fifth root. And so now what this means here, and you can notice, we can observe that 47 minus 15 is being contained completely inside the fifth root. And so what it means here is that 47 minus 15, even though not initially written, but this subtraction must be grouped. Okay, and then after grouping that, grouping indicates that, hey, after finishing out doing that grouped work right here, then we're going to take the fifth root on top of that at the end of that result right there. And so now after realizing that, then so again, grouping is to increase the order of operations. So now everything that's grouped inside parentheses is here will become the faster, but the order of operation. And so 47 minus 15 gives me a 32. And now taking the fifth root after, the answer will come out being 2. And that is simply because 2 to the fifth power equals 32. All right, so let me now point out a couple of remarks right here. So something for you to pay close attention to, and remember that remember that for any times that you're working with the root in general. So for square root, we've seen these remarks, and now I'm going to generalize that into nth root right here. But the nth root of a sum, a plus b, will generally not equal to the sum of two nth roots. Okay, because you can see that here these are in a more general settings right here. These are, see, this is, we're adding two separate roots. So it means we have to, according to the order of operation, we have to finish out taking the two roots. Here we have to group the a and b as a sum right here, group that sum, and then take the square root after. So there's no guarantee that the answer will come out equal. So generally it's not equal. Okay. As another general remark right here, taking the nth root of a difference is generally not equal to the nth root of a minus the nth root of b. Okay, so these are the remarks that we need to keep right here in case you fall into any of the mistakes. So the order of operation says we have to generally calculate the two separate roots here, then take the difference. Whereas over here, we are taking the nth root after finishing out the difference. So there's no guarantee that these two sides right here will come out with equal result. All right, so we have seen the following results back in the lessons about square root specifically. So generally for any square root of a square expression must come out equal generally the absolute value of a for all values of a, because here I've had all of those explanations back in the lessons about square root. So here I'm just briefly reminding it. So a here is an expression. And so furthermore, we came to that result that square root of a squared can equal to a without the absolute value, but only when a itself is greater than or equal to 0. So we have seen this result from the lessons about taking square root. We now have a corresponding result right here when we generalize that into some general nth root right here. So if n is odd right here, taking the nth root of a to the n, the idea now is that the power of the expression inside the root equals to the root order. So taking the nth root of the a to the n will equal a for all values of a if n is odd. So when n is odd, the nth root here is an odd root. It's easy. You can take the nth root of any n power and that comes out just simply a. Or we can think about, we cancel the and right here. Okay, the and root cancel with the and power inside, giving you a. But that's only easy when n is odd. Now, when it comes to n is even, if n is even, taking the nth root of a to the n power expression must come out with a in absolute value or equal to absolute value of a. Okay, and then as a further result, now if we restrict ourselves to strictly a is greater than or equal to 0, then this result right here will always be true. The nth root of a to the n will always be a without the absolute value. And then that's true for any given integer n, like that being the root order. So what you have seen just now on the computer screen is sort of like a generality about any time we're taking the nth root of a value, and we can generally rely on that method about we turn the expression inside of the root into some n power corresponding to the nth root right there, so that we can easily take the root operation. However, allow me to bring in another demonstration problem so that we can enhance our understanding, okay, and bring in some better methods on that. All right, so in this problem 2 right here, allow me to demonstrate a simple calculation problem, but it can be done in quite a few different ways right here, and then we're going to learn some more generality about how we are doing this. So, according to the information we have seen just now on the computer screen, then what we're looking at here is a cube root of 729, okay? And so, now if we can think of the cube root, so in one way, if we strictly stay with that guideline given on the computer, generalized on the computer screen right there, then we can think of the 729 here as a 9 cubed. Okay? 729 here can be thought of as a 9 cubed. Okay? And then we take the cube root. And so now this description here, this way of how we're writing it, matches perfectly with the way how it was expressed, with that generality being pointed out on the computer screen. And then see, before the cube, the value here is already a positive value. And so now the 9 to the third power, taking cube root of that, the answer will come out just being simply 9. Yes? So we in that one specific route right there, we can obtain the answer. Okay? But now let's roll back a little bit. Now, someone can come at me and ask, how did you come up with this? How did I come up with that so quickly? I mean, 729 is, expressed as a 9 to the third power. It's not easy for everyone. It took me years to realize that. Okay? And so now, if that route doesn't work too well, the point now is that, yes, ideally, we always want to express our expression inside of the root into the power n exactly matches with the nth order of the root here, so that it will come out just simply a, or depending on whatever the condition is, okay, that we've seen earlier. So ideally, that's the methods that we've been relying to. But now, what I want to point out in this problem is that, what if we don't recognize that power n to match with the nth order of our root so easily? What if we can't find that so easily? And so now keep in mind, for this particular problem right here, we already had an answer. That answer is 9, because it's 729 was thought of as 9 to the third power. But like I said, that going that way is not always so easy directly. Okay, so now let me show you an alternative, and it will come up with another generality for us to work with here. So let me bring in the prime factorization. So prime factorization is a skill that you must learn prior to entering this course right here. So 729, after prime factorization, we have the prime factor being a 3, but that can be raised to the 6th power. Because really the truth is, with the prime factorization process, 729 can be teared down as 3 times 243. So 3 here is already 1 prime factor. And then so 729 is a product of 3 and 243. All right, and further, 243 can be expressed as 3 times 81, but then with that other factor there. So now this whole 729 is understood as 3 times 81. 81 is further expressed as, and now we can rely on our natural sense here. And I'm briefly reminding about the prime factorization process. These are all the prime, so we chase for all the prime factors that exist in our beginning number over here. So 81 here is a 9 times 9. So sometimes we can just rely on our natural multiplication sense here. But 9 is not a prime, the other 9 is not a prime. So I'm thinking of each of these 9s right here as a 3 times 3 and another 3 times 3. That's why now that's 3 times 3 times that is a 3 times 3, and that is another times 3 times 3. And that's how I ended up with 1, 2, 3, 4, 5, and 6. Prime factor is 3. That's why 729 is expressed, can be seen as a 3 to the 6th power. Alright, so after seeing 729 can be expressed as a prime factor 3 to the 6th power, I can rewrite cube root of 729 as the cube root of 3 to the 6th power. The cube root of 3 to the 6th power. So I'm introducing a separate route right here in case we don't recognize the cube power, the third power that matches with this, the order, the cube order of the root right here. So now in this way, but see, what I'm seeing here is the 6th power here is not quite what we were looking for, just something that matches with the third order of our roots, but in the end the 6th power here that I'm seeing is a multiple of 3. Our root order here is a third order 3. And so the power here on that prime factor has a power being a multiple of 3, and it's a 2 multiple. It's a 2 multiple. So 6 is a 2 times 3. That's why I said it's a 2 multiple. So 6 is a multiple of 3. So here's how I'm seeing it. It's the same as cube root of 3. See, I'm taking advantage that 6 is a 2 times 3. So it means the power of 6 here can be expressed as a product 2 times 3. And so now with a little more algebra from our previous course, we can rewrite it as, so this cube root here, it's a 3 square, but I'm putting the cube outside. So now I have what I have expressed here. So the way how I go from this to that, you need to bring in your learning from the previous course. But now I have turned that into a cubic, a third power that matches with this third order of the root right here. So the answer here will come out being the 3 square, which will eventually become a 9. Right there for that. Okay. So the idea, one generality I'm looking for here now is that anytime we're taking some n root, some general n root of an expression, if we cannot find the immediate n root that's going to this number over here, what we can do is we can go through the prime factorization process and recognize the whole number here as a power being multiple of that n. So here it's cube root. I recognize the 3 here being raised to a power. I mean the 729 is equal to the prime factor 3 being raised to a power that is a multiple of that root order. The power 6 here being a multiple of that root order. And then so I can purposely rewrite that as, see, so now multiple of 3 right there, I write that as a cubic. And then that whatever the multiple we recognize that as, I put that as that's how I had it, a 3 square here. All right. So now recognizing the number inside the root as a power being the multiple of the root order, the power being the multiple of the root order, that will help a lot of times because we don't always recognize the power, the perfect power that matches with this perfectly, not so easily. Okay. All right, so now in this example 3 right here, allow me to apply that concept we have just learned, that generality we have just come up with from problem 2, from the demonstration problem 2 just earlier into this problem right here. So here we are asked to simplify fourth root of all of that fancy thing, 256 times x to the 4th times y to the 12th power right here. Okay, so how am I going to simplify something like this? And see, Ideally, it's best to recognize the whole thing here. The goal here is to recognize the whole thing as some expression to the perfect 4th power. That's the whole idea right there. But how do I arrive there? And what's the expression inside here that can be written as the 4th power so that we can easily take the 4th root. That's where the challenge comes in right here. So if we don't recognize, here I'm talking about, if we don't recognize the, how we can, if we can't recognize that that expression before taking the fourth power to arrive at 256 x to the fourth y to the 12 right here so easily, if we don't recognize that so easily, here's what we can do. So think about on scratch work. Here's my thought process. The expression inside the root, 256 x to the fourth, it's all product right here times y to the 12. Okay, let's handle the numerical part right here. So what I have here is 2 to the 256. Right? It's an even number, so I see it has a prime factor of 2 in there, times 128. Okay, so let's just slow it down, do the prime factorization process. 128 can be seen another even number, so I can see that as a 2 times 64. But then don't forget there is still that 2 from the earlier steps. So now it's 2 times 2 times 64. That makes 256 together. 64 is further seen as a 2 times 32. And then don't forget we have the other 2 factors right here of 2. And so now 32 is another even number. So I can see that as a 2 times 16. Okay, so now times 2, and times the other 2. So it's 2 times 2 times 2 times 2. 2 times 16. And then 2 to the 6, and then 16 right here, yes. We can see the 16 here, it's easy when it's reduced down to number easy enough, right? And I can see that this 16 right here is 2 to the fourth power, and then it's a prime factor to a power, and then multiply with these guys right here, making it another 2 to the fourth power. So all together, really, it's 8 factor of 2 altogether. So it's all of that is 2 to the 8th. Okay, so 256 is 2 to the 8th. I'm writing that in. Aside from that mind process right here, 2 to the 8th. That's how I express 256 as a prime factor being raised to a power. But this power now is a multiple of 4. It's a multiple of 4, some multiple of 4. Okay. The other factor in the group right here being a variable, I can just simply treat that as a prime factor itself. Now, to a power, this power is also a multiple 1, a 1 multiple of 4. And then the y to the 12 power, I'm seeing that as a multiple. These are all multiple of 4 now. These powers, these various powers, these are a multiple of 4. So now I'm seeing that here as a 2 to the 2 square to the fourth power, because we want to see multiple of 4, so that's multiple 2. It's a 2 multiple of 4. So I'm writing that as 2 squared to the fourth. This is just 1 multiple of 4. So I'm seeing that as just x, right, to the fourth power. Okay. And then this last one right here is a 3 multiple of 4. I'm seeing that as y cubed to the fourth power. Okay. And so now all together, this entire expression here is 2 squared times x times y cubed. All of these power before the fourth power, all of these factors before the fourth power, I can group them together and raise to an overall fourth power. Okay, and this is how I have recognized that 256, right? X to the fourth, y to the 12 power is recognized as 4x y cubed all to the fourth power. Okay, it was a long, lengthy process, but it will guarantee the correct result right here. And now after expressing that as a fourth power, now we can take the fourth root easily. Okay, and that's making it, and assuming that the x variables and the y variables are all the non-zero quantity right there, then we're looking at just simply 4xy cubed right here. Okay, and then let's say, assuming all variables, okay, are non-negative. Okay. And so again, I emphasize in this demonstration problem, a central theme is that sometimes when it gets challenging, then we can just simply, hey, if we're intending to look for to express our expression here as an overall power of n, then we look for some multiple of n amongst our powers so that we can come up with a final power n right there. Okay, so here it was, our beginning expression was all over, right? But we want to look for that as a something overall to the fourth power. So that's how I broke it down right there, and including the prime factorization process. And here I was hopefully just doing a brief review so that anyone can get your way back right there. All right, so now let's look at example 4 here, where we can apply that generality I brought up throughout the demonstration problems just now. So let's just now simply evaluate this. What we have here is a cube root. We take the cube root of this expression. It's a fraction of 320 over 5 here. Okay, so here in this example specifically, we can apply a lot of our generalities that we've picked up prior to getting into this example. So again, I'm seeing that the division here, it's a fraction, so it's a division. The division is grouped inside of our root expression, so that means we have to perform the division first. Okay, we have to perform the division first before we do anything else, before taking the root. And so now in that way, I'm seeing that as 320 divided by 5 gives me a 64. 320 divided by 5 gets me into a 64. And so now the next step is to take the cube root, because once again grouping is making it the highest order. So this division must be done first before the root. And so 320 divided by 5 gives me 64. And now this is the only remaining operation, taking the cube root of 64. So now in my next step, 64. Okay. One way of seeing it, we can see that as a 4 cubed, and then we take the cube root, and the answer will come out as easy as just 4. Okay, that's one way of seeing it. Now allow me to make that a separate route right here. So I'm talking about right after you have arrived at 64. It could have happened that we don't recognize 64 immediately as a perfect cube like that. So if you recognize that as a perfect cube of 4, to take the cube root perfectly, that's good. I'm talking about if we didn't recognize the 64 here as a perfect cube, we have a way to handle it. So to handle that situation, if we didn't recognize the 64 here as a perfect power that matches with this order, here's what we can do. 64 in as a prime factorization is a 2 times 2 times 2 times 2 times 2 times 2. Okay, that's how we did the prime factorization. So in the end, it's 2 as a prime factor raised to the 6th power. Okay, so let's write it down. So separately as a different route right here. Cube root of 64 can be done through prime factorization. Cube root of 2 to the 6th power. 2 to the 6th power. But so now 2 to the 6th power from that generality we have learned just prior to getting into this example. 2 to the 6th power, this power 6 right here is a multiple of, now our root right here is 3, so tentatively we're looking for that power being a multiple of 3. The root is 3, so that power here is at a multiple of 3. It is, right? It's a 2 multiple of 3. So I'm seeing that as, so now it's a 2 multiple of 3. So it's a cube root of, I said 2 multiple of 3. So now it's going to be 2 to the power 2 and then raised to the 3rd power. Okay, because 6 is a 2 multiple of 3. Okay. And so now in this way right here, we have recognized a perfect cubed expression right there. And so the answer comes out just 2 square. And 2 square once again comes back to being 4. The answer will be 4. Okay. All right, and in this example 5 right here, we're asked to simplify this 5th root of a very large expression right here. We got 1024x to the 13 y to the 17 divided by x cubed, the product of x cubed and y squared. Okay, and so we got variables involved, we got numbers involved, and powers on each of the variables right here, and it's a 5th root problem right there. Okay, so ideally we want to see this as a 5th root. And the idea, once again, I want to apply that generality we have learned prior to getting into example 4 and 5 here, that we want to express the entire fraction here as some perfect 5th power of some expression, the perfect 5th power of some expression. So what will be that magic expression there? Okay, and so now let's make our way here. So now first of all, here's how I'm seeing it. Fifth root. From what we've learned already as a generality up to this point right here, then in this problem right here, the division is completely contained inside the root. So that means as far as order of operation, we must do some division, okay, before we taking the root. And so looking at the division inside the root right here, there are a lot of cancellations algebraically that we can do right here. So I'm not going to rush into finding the fifth root. I am going to reduce. So x to the 13 divided by x cubed right here. So we can observe that x to the 13 will cancel nicely into x to the third power. Okay, and that will leave behind an x to the 10th. Okay. X to the 10th. Y to the 17 will cancel with y squared, leaving behind a y to the 15th power. So x to the power 10 and x to the y to the power 15. But all factors in the denominator have been cancelled away. So we have a remaining expression right here. Fifth root, and now we have 1024, x to the 10th, y to the 15. All right, so now we have simplified from a fraction inside of the roots into this. All right, so now the expression inside, once again, our goal is to look for the overall expression here to be expressed as a sum expression to the perfect fifth power, because our goal here is that we're doing fifth root here. Okay, so in order to successfully get there, right, this is what we do. The numerical part, 10024, is understood as 2 to the 10th power after prime factorization. Okay, and you can always double check me on that. Okay, 1024 is understood as 2 to the 10th power. So I'm rewriting that here. Fifth root, 1024 is 2 to the 10th power. Now each one of these powers from the x and y right here, the power 10 here is already a multiple. Well, let's rewrite it. Y to the 10, x to the 10th, y to the 15th. So now within all of these powers right here, these are all powers being some multiple of 5 right here. So now I'm seeing it inside of fifth root. 2 to the 10th power, I'm seeing the power 10 right here is a 2 multiple. The 2 multiple of 5. So 2 multiple of 5, I'm seeing that as 2 squared to the fifth power, because that number 10 right here is a 2 multiple of 5. That's why I'm writing that overall power here as a 2 squared, 2 multiple of 5. Okay, x to the 10th, right? I'm seeing that also as another 2 multiple of 5 right there. So I'm seeing that as x squared to the fifth power. The last one here, the power 15 right here, is the 15, we understand that as a 3 multiple of 5. So now I'm writing that y to the 15 as y cubed to the fifth power. And all that entire product is completely contained inside the root. All right. And so back to this board right here. See, we generally want to put some expression inside of that. Okay, as an overall power of 5. So we're close from getting there. So now, with this curtain step right here that we have here, it's now still a fifth root there, but now I can see these are all now I have expressed 2 squared to the fifth power, x squared to the fifth power, y cubed to the fifth power. So I have all of these to the fifth, to the fifth, to the fifth. So now I can write it all as a 2 squared times x squared times a y cubed. And then that common fifth power here can be just the final common power to the fifth power. Okay, and so we have made a long way from the very ugly looking fraction right here. We simplified it down to something like this. And then we recognize all of these powers as multiple of 5, multiple of 5, multiple of 5. And that's how I have re-expressed those. Okay, and so now I group the power of 5 all together into one power. And I have left behind 2 squared x times y cubed. and 2 squared is a 4. So now I'm ready to make my way back to the other board. So really, after so many steps to explain the reasoning, all of that here is broken down to 4x squared y cubed all to the 5th power. Okay, and so now my final expression. And you can think about, all of those earlier steps. You can fit it in before I arrive at the steps. Okay, and then now the next step after that. So now the 5th power being compensated together with that 5th root right here. They cancel out and they're making it 4x squared y cubed. And this is our final answer right here. All right.